Now we have to do some of the analysis. So now what I want you to do is for the parallelogram method and the tip-to-tail method, I would like you to cover up part of your diagram. So we're going to pretend at this point we knew that the three forces were in equilibrium because they were moving, right? So we had three spring scales all connected to that same white ring in the middle, and that white ring in the middle was not moving, which means the forces were balanced. So what we want to do is use two of the forces to make a prediction or verification of the third force. So we're going to cover up one of the forces. In this case, I'm going to use the Post-it note to cover up this force right here. I think that'll work. This one's going to go 2 centimeters to a Newton. So 2 centimeters to a Newton, which means the 3.8 newtons is going to be 7.6 centimeters in length. So along my proper direction, I'm going to now draw the line a little bit heavier. Line things up, be real precise, out to 7.6. There's 7.5 and there's 7.6. And when you draw the head of your arrow, don't make the line longer when you draw the head of the arrow. Just make sure you do that carefully. And then in this direction, it's 4.2 newtons, which means we're going to have 8.4 centimeters. All right, we're doubling that. So the rest of this line is just given the direction. We don't really need that, so I'm going to lightly erase the rest of that line. And now what we're using is called the parallelogram approach.
And these rulers are great for the parallelogram approach. You are going to draw a parallel line from this force, from this vector. You're going to draw a parallel line that touches the tip of this vector. And likewise over here, you're going to draw a parallel line from the tip of this that's parallel to that. Now you can eyeball it, but from the distance like this, you can say, this looks about parallel to this. But what can be helpful is to actually use your ruler, get this lined up real nicely, draw a nice parallel line here, just real lightly. And now, keep going over. Do another parallel line that up real nicely. Draw another parallel line real lightly. Now for this one, you want to get to the tip. Notice these rulers have you have an edge, you have a line, you have a line, you have an edge. So there's various lines to help you kind of eyeball a parallel line. So we got to get this edge of the ruler to the tip. And then we can use some of the other lines. Like this is almost exactly parallel to, on top of that one. So this is a very nice setup. And now I just nudged it a little bit. Let's get that lined up again. And now I can, taking into account the thickness of the pencil lead on the edge, I'm now going to draw this a little bit more heavily. I'm going to use a dotted line and just kind of extend out here a certain distance, right about there. Okay, so this line is parallel to this line. And I used a couple of ruler widths to get myself over there in a nice parallel line. I'm going to do the same thing for this one. Lay this down, draw a nice light parallel line here, then scooch the ruler over, draw a nice parallel line here. And then from the tip of this vector, I'm going to use this back edge here. I'm going to draw a parallel line. In this case, my previous line is almost right on top of this one, so it's a pretty easy one to spot. And then draw a dotted line. Hold that ruler nice and steady while you draw that dotted line. And then I take that away, and then this is now a parallel line to this one. They intersect right there.
So now we're going to draw the resultant. Go ahead and measure it too. So I'm going to draw it and I'm going to measure it. So here's the resultant, and that's 1, 2, 3, 4, 5, 6, 7. 0.1, 2, 3, 7.4. So it's 7.4 centimeters, which in newtons we then have, because of our scale, is, what are we at, 3.5, 6, 3.7. So we're at 3.7 newtons in this direction. So this is the resultant. Of these two vectors. Now, to check it, we now unveil our other vector. And so when we unveil this, we can see that it was 3.6 newtons, which is really pretty close, right? 3.6 compared to 3.7. The direction's off a little bit, but you can see that it's pretty close. So if we go ahead and do this. This should have been right out in this direction. So it wasn't perfect, but it wasn't bad either. Let's do the resultant in red. It just sounds like it should be red. There we go. And then this 3.6 off in this direction, that would be 3.6 would be 7.2 centimeters. So 7.2 is about right there, off in that direction. So now when you look at where it actually was with the spring scale and where our resultant was, you can see there's a little bit of error, but it's not terrible. Okay, the tip to tail method. We choose two vectors. We're going to cover one up. I think we're going to have to cover this one up based on what I'm seeing here. So we'll cover this one up. And we've got 7.9 newtons in this direction. Now 7.9 is going to take us all the way out to here. This one we cannot double. So this one needs to be, the scale for this one is going to have to be 1 centimeter is 1 newton. We didn't use that up here because it would have been tiny. It would have been half this size. But in this case, we're going to have to do that. So
7.9 newtons. From the dot there, I'm going to put the 7.9 on the dot. And then I'll go to the 0 mark. So that's the 7.9 newtons. I'll get that little extra arrow out of there, get the extra line out of the way. And then this is 5.3 newtons. So there's 5.1.2.3.
all right, here's the tip to tail method. So here is the it's tip to tail, tail to tip. Maybe tail to tip is a little bit more accurate. So what we're going to do is from the tip of this one, we're going to draw the tail of this one.
And we need to have an angle in order to do that. So this is where you want to use a protractor to kind of figure out that angle. So, and I've got these protractors in the back of the room. We're going to get this lined up so we're right there, in this case at 360, which is of course also the 0. And this has an angle of 10, 20, 30, 40, 50, 90, 100, 110, 120, 130.5 degrees is the angle that we have right there, 130.5 degrees. So over here, actually it probably would have been helpful to keep that line there, wouldn't it? So let's go ahead and extend that line back where it was. So over here, from the tip, we're going to draw the tail of this one at the same angle. And so we've got that lined up with the original orientation. And the 180's lined up to 0, so we're going to go around at 90, 100, 10, 20, 30.5. 130.5 is right there. And so now I'm going to, at 5.3 newtons, which is 5.3 centimeters, 7.9 newtons, which is 7.9 centimeters, I'm going to now draw from the tip, the tail, out to here. And this will be 5.3 centimeters. So from here to here, 5.3. 1, 2, 3, 4, 5.1, 2, 3. So that's now the tip to tail. I suppose I should have done that kind of in a dotted fashion, so we'll make that a dotted line.
So the resultant now is where this one ends up. So the resultant of these two, using the tip to tail, is going to be from the point of origin to where the second vector ends up. So I'm going to draw from the tip. This red pencil's a little bit fatter, so there we go. And that is 1, 2, 3, 4, 5. We're right at about 6. So I'll call that 6 newtons, which is 6 centimeters. And now we're ready to unveil. And our direction is really nice here. This is 6.6 newtons, and this is only 6. So we're off a little bit when it comes to the magnitude. Again, for verification purposes, we'll draw that last arrow to 6.6 centimeters would be right there. So when you look at it just with the eye, these look pretty good. You know, you can see that one slightly longer. The directions look almost perfect. You know, we're maybe only off by a degree. So that's not bad.